Hello everybody, thank you for joining me today. My name is Munam and today we're going to be looking at a different type of video. Today we're going to be looking at tackling all the most common circuit questions. So rather than introducing any new concepts now I'm going to be tying together, consolidating really a lot of electricity knowledge that you've gained over the past few videos. Now with electricity, the real only thing you can do to learn is to do all the questions as with any sort of physics or really science in general. So some things that you need to know for this video is to understand how current, voltage and resistance all vary in both series and parallel, because we're going to be looking at both those circuits in the following questions. So if you're ready for that, let's get right into it. Alright, so first let's have a look at resistance calculations, right? So for all of these questions, you'll really be given these resistors that are usually labeled, and then you'll be told to find out the total resistance. So in our first circuit here, let's call this circuit A, we can see that all of these resistors here are connected in series. So what's our resistor law for series? Well, that's just RT, that's the total resistance, is equal to R1 plus R2 plus etc. However many resistors there are. Here we can see that there are three resistors, so let's just label them R1, R2, R3. The order doesn't matter because all we're doing is adding them up now. So here, let's do that. So RT is equal to 30 plus 40 plus 50, which is equal to 120 ohms. That's something that you have to remember. You always have to put the units in, otherwise you won't get the mark. So that would be the resistance of all these, the total resistance of this circuit A here. Now let's have a look at circuit B. Now, parallel resistors often throw students off because the equation is a little bit weird. So here we have 1 over RT is equal to 1 over R1 plus 1 over R2 plus etc etc etc. Okay, so a lot of students, they're fine with this part here, but they get confused right over here. So what do we do to that? So well, let's input all of these numbers first. So here we have 1 over 30 to 1 over RT, so 1 over 30 plus 1 over 40 plus 1 over 50. So this actually all ends up adding up to 0.0783. Now in physics we tend to always keep all of your calculator values that fall out in their full form. Don't round as you're doing calculation, always round right at the end, because if you round halfway through your calculation, that carries an error that could throw off your final answer. So 0.0783 is actually 1 over RT. So to convert this into just RT, we do 1 over 0.783, and that gives us 12.77 ohms again, and that is your final answer right there. So now I hope you understand how to calculate the total resistance of a circuit in both series and parallel. Alright, so now let's have a look at what is probably the most complicated amateur example you'll get in your entire GCSE. But if you can tackle this, you can tackle any question. So let's go right into it. Here we have a table full of the numbers of the ammeters and the current flowing through them. So to make our life easier, let's label these values on the actual diagram itself. So ammeter 2 is 4.8 amps, so A2 here, 4.8 amps. Ammeter 3 and 4 are both 4.2 amps, so ammeter 3, 4.2 amps, ammeter 4, 4.2 amps. Now, with these values, we can actually calculate all of the currents flowing through the other ammeters with one simple rule, and that is current flowing in a closed loop must all sum. Now, what does this mean? This means that the current going in to a circuit must also equal the current going out. So say 10 amps flowed from the circuit this way, 10 amps would also have to flow back into the cell the other way. Okay, so with that one principle, we can work out the rest of the amps. Now, in parallel, we know that current is shared. Okay, so say current is traveling this way, right? So we're looking at conventional current. So we say positive, actually, you know what, let's do it in blue. Say it's traveling this way, conventional current from positive side, remember the long side is positive, to negative. Okay, so current is flowing that way around the circuit. So current flows here, Okay, and now at this junction, so that's what you call like a joint, some of the current gets shared off that way and the rest goes that way. But the key is how much. Well, we know that ammeter 4 is 4.2 amps. That means that along this junction, 4.2 amps flowed, because again, like I said, currents have to sum. So if 4.2 enters, 4.2 also has to exit that way. Okay, so we know that that's 4.2, and we also know that ammeter 2 gives us 4.8 amps. Okay, so what's the remaining amps that must have been going into this entire thing? So all we have to do is add them two together, right? Because if 4.2 is directed this way, the remaining 4.8 has to be directed this way. But this all came from a larger current, so we just do 4.2 plus 4.8, which just ends up being 6.0 amps. So flowing into 6.0 amps. So flowing into A1 must be 6.0 amps. All right, I hope that makes sense. Now, we see here that 4.8 flowed down this way and 4.2 was taken off at a junction. Okay, so now again, this 4.8 has to be shared one way to A3 and another way to here. So all we have to do is work out the difference. What are the remaining amps? So we just do 4.8 minus 4.2, which is 0.6 amps. Okay, so for 0.6 amps are flowing in through here, then there, then there, then there, into A5, and then out of A5. So what would the reading be on A5? Well, that's just 0.6 amps. And well, we should really be filling these in into our table, so let's do that. So we worked out that A1 is 6.0, and we worked out, so we already knew that A2 was 4.8 and A3 was 4.2. So we found out that A5 is 0.6. Okay, so now we know that 4.2 amps are traveling along here, and this joins up with the 0.6 coming out from A5. So to work out what's traveling along here, all we do is 4.2 plus 0.6, which ends up being 4.8 amps. And as you can see, that's exactly what the amperage is on the other side of the loop, which should be exactly the same. So we have 4.8 amps here. Now, these 4.8 amps now join in with the 4.2 coming out of A4. So then we just do 4.2 plus 4.8, which ends up being 6.0 amps. So A6 is giving us a reading of 6.0 amps, exactly the same as A1, which is on the other side of the loop. So then that goes here, here, and back into the cell. So we know that 6.0 amps left the cell and 6.0 amps entered the cell. So that means that our condition here, that current flowing in a closed loop must sum, is true. So I hope you understand all of that. If you didn't, please go through the video again and work through it step by step. Or you always want to label your diagram in your GCSE exam, because it just makes the train of thought much easier to follow. Now let's have a look at our voltage example. Here we have 5 resistors, and we have to work out the voltage across all of them. Okay, where we can see 3 voltmeters in parallel, as they always should be, because they're measuring voltage across a component, across a cell, which is 10 volts, across R3, which is 3.2 volts, and R5, 4.8 watts of volts. Okay, so let's fill in our our table with all the known values. Okay, so we know that resistor 3 is 3.2 volts, and we know that resistor 5 is 4.8 volts. But the rest is up to us to work out. Okay, so let's have a look at resistor 1. Let's look at the loop resistor 1 follows. So we know that conventional current flows from positive to negative. Okay, so it goes here, down there, down there, down there, down there, down there. Okay, so this shows us that R1 is in parallel with the cell itself. So, and we know that the voltage loss for parallel is that the voltage across parallel components is exactly the same. So if the cell is 10 volts, R1 is also 10.0 volts. Okay, now we see that. Now, okay, so again, as always, let's mark that on our diagram so we can follow our train of thought much easily. So actually, let's just leave at 10 volts. Okay, that's fine. Now, can you see that R1 and R2 are also in parallel with each other, right? Because they follow a closed loop like that. These 2 resistors are also parallel. So again, by that same logic, R2 must also have 10 volts across it. So again, let's do that, 10.0 volts. Now, here's the tricky bit. Although there is another parallel combination, the next parallel combination is all three of these resistors with R2. So this tells us that all three of these resistors, so R3 plus R4 plus R5, these should equal 10.0 volts. Okay, and now we already know that R3 and R5 are their voltages respectively. So all we have to do is 10 minus 3.2 minus 4.8, which ends up being 2 volts. 2 volts remaining. Okay, so the remaining resistor is just R4. So the voltage across R4 must be 2.0 volts. And now if you understand that, you understand how to calculate voltages in parallel and in series. Because remember, R3, R4, and R5 are all in series. Remember, serial, they're connected one after the other, one after each other. Now we're going to do a combination of all three of these. So calculating resistance, amps, and voltages in one single question, as is very common in the GCSE exam. Okay, so now let's have a look at a hard example. As always, we're going to highlight all of our keywords. A student set up the electrical circuit shown in the figure below. Okay, the ammeter displays a reading of 0.1 amps. So as always, let's label that on our diagram just so it makes us easier to follow our train of thought. 0.1 amps. Calculate the potential difference across the 45 ohm resistor. So that's this one over here. Okay, so PD. So what equation do we use when we want to work out not velocity, voltage? V is equal to IR. That's the equation that we use. And we have I, which is the amps, and we have the resistance, which is 45. So all we want to do is multiply 0.1 by 45, and that gives us 4.5 volts. That's our answer right there. Okay, so let's tick that off. Next, calculate the resistance of the resistor labeled R. So that's what this one over here. Okay, that's fine. So first of all, the first thing that we can do is work out the current flowing through all of these components. So resistor R, let's have I and let's have V flowing across it. Okay, so because this is a series circuit, we know that there is 0.1 amps flowing across it, and series circuit current is always the same. It's the voltage that's shared in the series circuit, but the current is all the same. So we know that it's 0.1 amps across R, 0.1 amps across 60 ohms, and 0.1 amps across 41 ohms. So we can fill in as 0.1 amps. Okay, now we want to know how much voltage is flowing across this. So as per our circuit laws, we know that if 12 amps leaves the cell, 12 amps also has to enter back into the cell. And we've already worked out that the 45 ohm resistor has 4.5 volts across it. So let's take that away from 12. So 12 minus 4.5, that gives us 7.5, I believe. Let's do that quickly. 12 minus 4.5. Yes, 7.5 volts there. Okay, so now we also have the 60 ohm resistor, but we know already that the 60 ohm resistor has 0.1 amps across it, and using our equation V equals IR, we can work out how much voltage is across the 60 ohm resistor, which is just 0.1 times by, actually let's do it in red and on the side here. So 60 ohm resistor is equal to 0.1 times by 60 ohms, because remember that's the amps and that's I and 60 is R, so that gives us 6 volts. So now we have to take away 6 from 7.5 up there, so 7.5 minus 6, and that gives us 1.5 volts remaining, which is the voltage across R. So the voltage across R is 1.5 volts. Now we want to work out resistance. V equals IR, so we rearrange that for R, which is V over I, and that gives R. So we do 1.5 over 0.1, and that is 15 ohms. Okay, Oh, well, I don't even need to write ohms because it's written on the answer line. But that is our answer for number 3. I hope you understand. Okay, now let's have a look at the what I could argue is the hardest bit of the question. State what happens to the total resistance of the circuit and current through the circuit when switch S is closed. Okay, so switch S is open right now. What happens when it's closed? So we know that electricity always follows the path of least resistance. Okay, so if the switch S is open, the electricity will flow from here, through here. But rather than going through the resistor, which is resistive, it just goes through the less resistive wire. Because remember, switch S will be closed and it'll just bypass this resistor entirely, going here and back. So now, rather than having R here, plus the 60 ohm resistor, plus the 45 ohm resistor, we just have R, which is 15 ohms, and the 45 ohm resistor. So the total resistance has decreased. So I'll write here, total resistance decreases. But now, what is resistance? Resistance just tells you how the pushback against the flow of current. Now, if total resistance has decreases, there's less pushback on the current, which means that more current can flow. So current increases. And that would be another 2 marks right there. I hope you understood all of that.